This mini physics lecture is an introduction to energy, types of energy. Energy. Energy is like the money of the universe. Energy is defined as the capacity to do work, which is something that I'll explain in my little lecture on the work-energy theorem. Some things you need to know about energy. Energy is a scalar. So it doesn't have direction. It doesn't make sense to talk about the direction of energy. And the units of energy are the joule. Joules are abbreviated a capital J. And a joule is the same thing as a kilogram meter squared per second squared. So why is it called a joule? Well, it's named after this guy, James Joule. He gets the honor of having the unit of energy named after him because he proved that energies transfer from one type to another. He did experiments at a time when people recognized different types of energy in the universe, but they didn't realize that all forms of energy add together to make a total amount of energy, which is always the same in the universe. And so you can't create energy and you can't destroy energy. Instead, when you have one type of energy, like thermal energy, that decreases, it's going someplace else. It's being transferred into some other kind of energy, say kinetic energy, which is the energy of motion. James Joule proved this about energy using an apparatus like this. It's a little bit like an egg beater. So what happens is you put kinetic energy into it. You make these blades at the bottom move, and if this is submersed in a fluid, you can actually make the temperature of the fluid go up, which is an increase in thermal energy. And so James Joule proved that this form of mechanical energy, the spinning blades, was transferring energy into thermal energy, which was a little bit mysterious. It still is a little bit mysterious, actually. So let's talk about some of these specific types of energy. So first off, to recognize different types of energy, let's talk about three broad categories of energy. So energy can be kinetic energy. This is the energy of motion. Energy can also be potential energy, which is stored energy. And finally, there's radiative energy, which is light. Kinetic energy and potential energy are broad energy categories that have lots of subtypes, types of kinetic energy and types of potential energy that are going to be important for us to discuss as regards physics. Light also has some interesting stuff about it, but we're not going to talk about it at this time. All objects in motion have kinetic energy. We use the symbol K for kinetic energy, and an object's kinetic energy is proportional to its mass and to its velocity squared. There's a 1/2 in the equation, so to calculate an object's kinetic energy, we take 1/2 times the object's mass times its velocity squared. For objects which are rotating, there's a special form of rotational kinetic energy. We also use the symbol K, but we put a subscript ROT for rotation on there. Now this has a very similar form to the linear kinetic energy. 1/2 times I, which is the moment of inertia, times omega, which is the angular velocity squared. So notice that in linear kinetic energy, if you double an object's mass, you double the kinetic energy. If you double the velocity, you quadruple the kinetic energy because the velocity is squared. For rotational kinetic energy, doubling the moment of inertia will produce twice the rotational kinetic energy. Doubling the angular velocity will produce 4 times the rotational kinetic energy. A final important form of kinetic energy is thermal energy. We use a capital E with TH for thermal energy. Thermal energy is really related to the motion of particles within an object or within a substance. The particles inside objects, or in like a liquid or a gas, are in motion. They vibrate, they rotate, and they move around. The speed with which they vibrate, rotate, and move around is what contributes to the amount of thermal energy in that substance or in that object. There's some different ways to measure thermal energy. Heat and temperature are some of the ways that we can do it. The field of thermodynamics has to do with the transfer and measurement of thermal energy. There are several important forms of potential energy. One of them is illustrated by the image here, which shows batteries. Electrical potential energy. U is a standard symbol for potential energy, and a U with an E can stand for electrical potential energy. There are equations that deal with electrical potential energy, but I'm not going to go into them here. Another interesting place where you might find potential energy, and maybe you haven't realized it before, is mass. So the amount of potential energy, which is stored in mass, E, is equal to the amount of mass times the speed of light, c, squared. E equals mc squared is a statement of the amount of energy stored up in mass. Now, a couple of forms of potential energy that I am going to give you equations for because we'll be using them as part of our unit on mechanical energy are gravitational potential energy. So we use a U with a small g to represent gravitational potential energy. And the amount of gravitational potential energy that an object stores is equal to the object's mass, m, times the local gravitational field, lowercase g, that's also the acceleration due to gravity, times a vertical displacement within that field, delta y. Now the delta y is a little bit ambiguous because it's not exactly clear where zero potential gravitational energy is. This delta y lets us set our own 0 point. So if you're solving a problem about a child going down a slide, the bottom of the slide can be 0 gravitational potential energy. If you're solving a problem about someone digging a tunnel down into the earth, then the bottom of the tunnel can be your 0 point for gravitational potential energy. This delta y gives us some flexibility in suiting the equation for gravitational potential energy to the situation or problem that we're working with. The other form of mechanical potential energy that we'll be working with is spring potential energy. So again, I'll use the capital U and I'll put an S subscript on for spring. So the potential energy that can be stored up in a spring is equal to 1/2 times K, the spring constant, times delta X, which is either the compression or extension length of the spring, squared. In summary, there are a few different types of energy that you need to be familiar with. Kinetic energies. There's linear kinetic energy due to the velocity of an object. If an object's rotating, it also has rotational kinetic energy. Thermal energy is a form of kinetic energy because it's related to the motion of particles. Electrical potential energy is the type of energy stored in batteries. Mass is actually a form of potential energy. Gravitational potential energy depends on an object's mass, the gravitational field, and a displacement vertically within that gravitational field. Spring potential energy depends on the spring constant and the square of the displacement, either compression or extension of that spring. Finally, it's a good idea to keep in mind that radiative energy, light, is a form of energy. Energy is a scalar. It has units of joules, which are kilograms times meters squared per second squared. And that's the end of this little lesson.